everyone.
Hello everyone.
I am Himanshu
I am
Mishra,
Himanshu Mishra,
and in this
and in
tutorial
this
I am going to
tutorial I am
solve a
going to solve a
question
question
based on the
based on the
kinetics.
kinetics.
So we
So we
started
started
in this course,
in this course,
and at the
and
starting
at the
we actually
starting we
looked
actually looked
the statics
the
problem
statics
where we
problem,
actually
where
do
we
the force
actually do the
balance
force balance
analysis,
analysis,
and by
and
doing the
by
force
doing the
balance
force
analysis
balance
we
analysis,
actually
we actually
calculate the
calculate the
various
various
reaction
reaction
forces,
forces,
various unknown
various
external
unknown external
forces,
forces,
and so on.
and so on.
And then we
And
move to
then we
the
move to the
kinematics where
kinematics,
we
where
have
we
given
have given
uh,
uh,
any of the
any of
quantity
the
like
quantity like
velocity or
velocity or
acceleration or
acceleration
distance,
or distance,
and by
and by
kinematic
kinematic
equations
equations
we
we
actually
actually
try to find
try
out
to
the
find
unknown
out the unknown
acceleration or
acceleration or
unknown
unknown
displacement or unknown
displacement or
velocity.
unknown
So
velocity. So
basically
basically
what we have
what
done,
we have done,
that
that
we have given
we have given
displacement,
displacement,
velocity and
velocity and
acceleration,
acceleration,
and at
and
some
at
specific
some
time
specific
or at
time or
a
at
specific
a specific
distance or
distance or
displacement we need
displacement
to
we
figure
need
out
to
the
figure out
velocity
the
or
velocity or
acceleration.
acceleration.
And
And
this is
this is
uh,
uh,
we have
we have
this is
and
what we have
this is
done in
what
the
we have done in the
kinematics
kinematics
portion.
portion.
But now
But
we
now
are moving
we are
ahead with the
moving ahead with the
kinetics,
kinetics,
where we actually
where we
combine
actually
the
combine
static
the
part
static
where we
part,
have done the
where we
force
have done the
balance
force balance
analysis,
analysis,
and the
and the
kinematics part
kinematics
where we
part,
have
where we have
actually
actually
explored how to
explored how
calculate
to
the
calculate
velocity
the
or
velocity or
acceleration.
acceleration.
The only
The
difference
only
is
difference
here
is
the
here the
forces are not in
forces are not in
equilibrium,
equilibrium,
and that's why
and
when
that's
you
why
apply
when
the
you
external
apply the
forces,
external forces,
what happens? The
what
body
happens? The body
displaces.
displaces.
It has some
It
certain
has some certain
velocity, it may
velocity.
have
It
some
may
certain
have some certain
acceleration,
acceleration,
and
and
given the knowledge of
given the knowledge of
forces or
forces
given
or
the
given
knowledge
the
of
knowledge
velocity
of
or
velocity or
acceleration, we have to
acceleration, we
find the
have
other
to find the other
quantities.
quantities.
So for
So,
example,
for
there
example,
is one
there
class
is
of
one
problem
class of problem
where we have
where
given
we have
the
given the
nature of
nature
external
of
forces,
external forces,
and we are
and
required to
we are
find the
required to find the
velocity,
velocity,
acceleration or
acceleration, or
displacement.
displacement.
And then there are
And then
second
there are
class of
second class
problems
of
where
problems
we
where
have given
we have
the
given the
kinematics
kinematics
variables like
variables like
velocity,
velocity,
acceleration, and
acceleration, and
displacement,
displacement,
and then we need to
and then
find
we
the
need to find the
unknown external
unknown
forces
external
or the
forces
normal
or the normal
reactions,
reactions,
or it might be
or
a
it might
friction
be a
force as
friction
well.
force as well.
And
And
we combine
we
these,
combine
I mean,
these, I mean,
we combine
we
these two
combine these
things
two things
with each other
with each other
by
by
Newton's second law.
Newton's second law.
So before
So
diving into
before
the
diving into the
problems,
problems,
we will be
we
using the
will be
Newton's
using the
second
Newton's
law
second law
to actually
to actually
combining the
combining the
dynamic quantity
dynamic
like
quantity
force
like force
with the
with the
kinematic quantity
kinematic quantity
like a
like a
velocity,
velocity,
acceleration, and
acceleration,
so on.
and so on.
So as per the
So as per the
Newton's second law,
Newton's second law,
if
if
there are multiple
there are
forces
multiple
like
forces
F1,
like
F2,
F1,
F3,
F2,
and so on,
F3, and so
and
on,
these forces
and
are
these forces are
collinear with each
collinear
other,
with each other,
then what
then
happens
what
that the
happens
summation
that the
of
summation of
this force
this
can be
force
written
can
as
be written as
mass into
mass into
acceleration.
acceleration.
And we will be
And we will
using
be using
this formula
this formula
to actually
to
evaluate
actually evaluate
either of these
either of these
quantities.
quantities.
So
So
let's begin with the
let's
first
begin with the
problem.
first problem.
So in the first
So in the
problem,
first
we
problem,
have the
we have
400
the
kg
400
mine.
kg mine.
Car is
Car
hoisted
is
up the
hoisted up
incline
the
using the
incline
cable
using the
and motor
cable
M.
and motor M.
For a short
For
time,
a short time,
the force of the
the
cable
force of
is
the cable
F
is F
3200 T square
3200 T
Newton,
square Newton,
and here T
and
is in
here T is
seconds.
in seconds.
If the car
If the
has
car
initial
has
velocity
initial
V1,
velocity
which is
V1,
2 meter
which
per
is 2
second,
meter per second,
at
at
displacement 0 and
displacement
time
0
0,
and
we
time
need
0,
to
we need
determine the
to determine
distance
the
it moves
distance it moves
up the plane
of the
when time
plane when
equals
time
2
equals
seconds.
2 seconds.
So here
So
we have
here
given the
we have
force,
given the force,
which
which
is a function
is
of
a
time.
function of time.
And we have given the
And we have
initial
given the
velocity
initial velocity
2 meter per
2 meter
second
per second
at
at
distance 0
distance 0
and time
and
0 of
time
course,
0 of course,
and we need to
and
find
we
the
need to find
distance
the distance
at
at
time
time
2 seconds.
2 seconds.
And we have
And
given
we
a
have given a
figure here,
figure here,
and from this
and
figure we
from
can
this figure we
actually
can actually
easily
easily
make a free body
make a free
diagram.
body diagram.
Let's say this is
Let's
a
say this is a
schematic of a
schematic
car,
of a car,
and this is
and
the
this
weight
is
of the
the
car.
weight of the car.
and this is the
This
force
is the
acting, which
force
is
acting, which is
3200 T square.
3200 T square.
And this is my
And
normal
this is my
reaction.
normal reaction.
And that's it.
That's it.
And we have given the
And we have
angle
given the angle
here, which
here,
is
which is
here it is
here it
17,
is 17,
here it is 8,
here it is 8,
and here it is
and here
15,
it is 15,
which means
which
that
means that
here it will be
here it
8,
will be 8,
15,
15,
and 17.
and 17.
So some
So
angle.
some angle.
So
So
now what we
what
can do,
we can
since
do,
we have given
since
the
we have
force
given
and
the
we need to
force,
figure
we
out
need to
the
figure out the
kinematic quantities. Like here we need to
Here
figure
we
out
need
the
to figure out
distance.
the distance.
First,
First,
we need to do the
we need
force
to do the
balance
force
analysis,
balance
and we
analysis, and
from the force
from the
balance
force
analysis,
balance
what we
analysis,
can
what we
check
can check
what are the
what
unknown
are the unknown
forces
forces
are there in the
are there
system.
in the
For
system.
example,
For
as of
example,
now we have
as of
three
now we have
forces:
three
W,
forces:
which is
W,
weight,
which is weight,
and the given
and the given
force from the
force
cable,
from
which
the
is
cable, which is
3200 T
3200
square,
T
and
square,
one is the
and
normal
one is the
reaction.
normal reaction.
And
And
one can
one
suspect
can
that the
suspect
normal
that the
reaction
normal
is the
reaction
unknown
is the
force.
unknown force.
So when we do
So
the
when
force
we do the
balance
force balance
analysis, let's
analysis,
say I'm
let's say
taking the
I'm
coordinate
taking the
system
coordinate system
along the inclined
along the
direction
inclined
x and
direction
y.
x and y.
So it's always
So it's
advisable
always
to
advisable to
do first the force balance analysis, because from the force balance analysis we will get clear how to go ahead. So
So
in the x
in the
direction,
x direction,
so here I will
so
be
here I
using
will be
the
using the
Newton's second law,
Newton's second law,
and let's say my okay, I will come to this later.
later.
So
So
if I do the
if
force
I do the
balance
force
analysis
balance
in the x
analysis in the
direction,
x direction,
x and this is
x
y.
and this is y.
So I have
So I have
3200 T
3200
square.
T square.
I have the
I have
component
the
of this
component
weight.
of this weight.
That's it.
That's it.
So it will be
It will be
3200 T
3200
square
T square
minus
minus
weight, which is
weight, which
400,
is 400
multiply
multiply
by
by
9.81
9.81
multiply by
multiply by
8 by 17, which is a
17, which is
component
a component
in the x
in the
direction,
x direction,
which is
which
ME,
is ME,
mass into
mass into
acceleration.
acceleration.
So it is
So it is
400
400
A.
A.
So we can
We
simplify
can
this
simplify
equation.
this equation.
So here I will be getting 3200 T square
T
minus
square minus
1846.588 equals 400 A. So my A will be minus 4.6164 plus 8T square. So this is the expression I got when I did the force balance analysis in the x direction, and one can see that we got the relation of acceleration, which is a function of time. And since the acceleration given in terms of time, we can use a relation where velocity can be where the acceleration can be given as rate of change of velocity. So I can write dv as a dt. So if I integrate it from 2, which is my initial velocity, to some v, and from 0 to time, I will get v minus 2 equals 8t square. Let me write step by step. So I will have 8t square minus 4.616 dt
from 0
from
to
0 to t,
and on
and
integration
on
I will
integration
get
I will get
v minus
v
2
minus 2
equal
equal
8
8
t
t
cubed by 3
by 3
minus
minus
4.616
4.616
t.
t.
So this will be
This will be
2.66
2.66
t cube
t
minus
cube minus
4.616 t.
4.616 t.
So my
So my
velocity
velocity
again
again
is a function of
is a
time,
function of
and
time,
it will be
and it
2
will be
plus
2 plus
2.66 t
2.66
cube
t cube
minus
minus
4.616 t.
4.616 t.
And this is
And
my
this is my
expression for
expression
velocity
for
with respect
velocity
to
with
time.
respect to time.
But we need to
But
find
we
the
need to find the
distance
distance
at time
at
equal 2
time equal 2
seconds.
seconds.
So
So
here
here
I can write
I can write
velocity as
velocity as
rate of change of
rate of change of
distance or
distance
rate of
or
change of
rate of change of
displacement actually
displacement
with
actually
respect to
with
time.
respect to time.
So
So
I can write
I can
as
write as
I can
I
integrate the
can
above
integrate the
expression
above
again
expression again
from 0
from
to
0
s
to s
from 0
and
to
from
time.
0 to time.
So it will be
So it
s
will be s
equals
equals
2 plus
2 plus
2.66 t
2.66
cube
t cube
minus
minus
4.6
4.6
t
6t
dt,
dt,
and on
and on
integration I will
integration
get
I will get
2t
2t
plus
plus
2.66
2.66
t4 by
t4
4
by 4
minus
minus
4.616 t
4.616
squared
t
by 2.
square by 2.
And here we
And
need to
here we
plug
need to plug
t equals
t
2
equals 2
to find
to
this
find this
displacement at a
displacement at
specific
a
time, which
specific
is t
time, which is
equals to
t
2.
equals to 2.
So
So
at t
at
equals
t
to 2 I
equals to
have
2 I have
2 multiply
2
2
multiply
plus
2 plus
2.66
2.66
minus
minus
4.616 2
4.616
square
2 square
by 2.
by 2.
So when I
So
solve
when I
this, I will
solve
get
this, I will get
displacement at time
displacement at
t
time
equals
t
to
equals to
will be
will be
5.4
5.4
meter.
meter.
So this is
So
my
this is my
answer.
answer.
So just to
So
recap,
just to recap,
here we have
here
given
we have
the
given the
400 kg
400
car
kg car
and which is
and
trying
which
to
is
go
trying to go
ahead in the
ahead in
inclined
the
plane,
inclined plane,
and we have given the
and we have
force
given
due
the
to the
force due
cable,
to the cable,
and then
and
we have given
then we
the
have given the
velocity at an initial
velocity at the initial
condition,
condition,
and we need to
and we
determine
need
the
to determine the
displacement at time
displacement
t
at time
equals
t
2
equals
seconds.
2 seconds.
So first
So first,
we have done the
we
force
have done the
balance
force balance
analysis, and
analysis,
for
and
that we have
for
used
that
the
we have
Newton's
used the
law.
Newton's law.
Here,
Here,
the summation of
the
all the
summation of all
forces
the
is equal
forces
to
is equal
mass
to mass
into
into
acceleration,
acceleration,
and we did the
and
force
we did the
balance in the
force
x
balance in the
direction
x
only.
direction only.
And from this
And
force
from this
balance,
force balance,
we actually
we
get the
actually get the
expression
expression
of
of
acceleration, which
acceleration,
is a
which
function
is
of
a
time.
function of time.
Now, in order
Now,
to
in order
calculate
to
the
calculate the
distance,
distance,
what we did,
what we
we
did,
actually
we
first
actually
calculate the
first calculate
velocity,
the velocity,
which
which
given
given
as
as
sorry, which
sorry,
is given
which is
as
given as
in terms of
in terms of
acceleration and time.
acceleration and time.
And to find the
And to
velocity,
find the
we need to
velocity, we
integrate
need
this
to integrate
expression.
this expression.
Then once we get the
Then once we
velocity
get the
expression,
velocity
we again
expression, we
integrate
again integrate
in order to
in order
calculate the
to calculate
distance.
the distance.
So in this
So
example,
in
you
this
can see
example, you
that
can
how
see that
we
how
actually
we
connect
actually
the
connect the
force
force
or the dynamic
or the
quantity
dynamic quantity
into a
into
kinematic
a
quantity.
kinematic
So
quantity.
first we
So first we
do the force
do the
balance
force balance
analysis,
analysis,
and then from
and
that
then
we
from
actually
that we
got the
actually got the
kinematic quantity, and
kinematic
we
quantity,
actually
and we actually
found another
found
kinematic
another
quantity
kinematic quantity
by the
by the
existing equation.
existing equation.
So we will be
So we
solving
will be
such
solving
questions
such
more.
questions more.
So
So
let's
let's
move to the next
move to the
question.
next question. So the next question is also pretty much similar, and here also we need to approach in the same way that we have done before. So the question is, if the motor draws the cable at a rate of velocity which is 0.05 s to the power 3 by 2 meter per second, where the s is in meters, determine the tension developed in the cable when s equals 10 meter. The crate has a mass of 20 kg, and the coefficient of kinetic friction between the crate and the ground is 0.2. So here the box or the crate is moving with a velocity which is a function of distance s, and we need to find the force when the distance between the crate and the cable is 10 meter, and we have given the mass of a crate which is 20 kg, and we have given the coefficient of friction. That means there is a friction force also which is acting as the crate is moving toward the cable. So the velocity we have given is a function of distance 3 by which is 0.05 s to the power 3 by 2 meter per second. Now, in order to do the force balance analysis, it is clear from the above problem that the force can be written in terms of mass into acceleration. So if we want to do the force balance analysis, we need the acceleration here. And clearly in the question we are given the velocity which is a function of distance. So from this expression we actually calculate the acceleration, and then we can use that expression of acceleration to do the force balance analysis. And by the force balance analysis we can actually calculate the unknown force, which is tension in this case. Well, the friction force is also the unknown force here. So since here the velocity given is a function of distance, we can write the acceleration as v dv by ds. And this expression in the earlier class I actually explained how we got this expression. So for example, let's say I can write the velocity as rate of change of displacement, and the acceleration can be given as, let me write in the scalar form, rate of change of velocity. Now if I eliminate the dt here, I can write the above expression as ds by v, and here dv by a, and I can equate these two expressions with each other. And then the acceleration will be v dv ds. So this is the expression we are using because we have given the velocity in terms of distance. In the previous question it was given, we actually obtained the expression of acceleration in terms of time. So we use this formula, but now it is given in terms of distance, so we will be using this one. Now if I differentiate, I will get So this is the expression of acceleration we actually got, which is given in terms of a distance. And you can see that this box is actually moving in the horizontal direction, and the velocity of that this box is actually a function of distance. And here we got the acceleration, which is also a function of distance, and it is moving in the horizontal direction, which means this is the horizontal component of the acceleration. Because since the box is not moving in the vertical direction, the acceleration in the vertical direction is zero. This is my horizontal component of acceleration. Now we can do the force balance analysis because we got the acceleration. So, for example, let's make a free body diagram first. This is my weight. This is my normal reaction. This is my friction force. And this is the tension force. And if I do the force balance analysis, the vertical direction, and we can see that the acceleration in the vertical direction is zero. So it is zero. So basically, it is summation of force in the vertical direction equal to zero. And it is quite similar to what we have seen in the previous classes when we are solving the static questions, where we were doing the force balance analysis, and when all the forces are in equilibrium. So here vertical component of the force are in equilibrium, which means that the normal component or the normal force is balancing the weight equal to zero. So the normal force will be, which is equal to weight is mg. So my normal force is 20 multiplied by 9.81, which is 196.2 Newton. Now if I do the force balance analysis in the horizontal direction, then I have tension force and the friction force equal to ME. I can write the friction force in terms of normal force, which we found earlier, equal to M, and my acceleration was 0.00375 s square. And my coefficient of friction is 0.2 multiplied by 196.2. And we need to find the tension at distance 10 meter. So here we need to plug S, which is 10. So my tension is 46.7 Newton. So this is the unknown required force we need to calculate. So just to recap here, we have given the velocity, which is a function of distance, and we have given the weight, we have given the coefficient of friction as well, and we need to find the unknown tension force here, which is exerted from this cable. So for this, first we figure out our intention to write the equation from the Newton's second law, and we figure out that in order to do that we need to first define the acceleration. And since we have given the velocity in terms of distance, we actually use kinematic equation in order to define the relation of acceleration with respect to the distance. And once we got the acceleration, we actually did the force balance analysis to calculate the unknown required force. So from the vertical component of the force balance, we actually found the normal force, and from the horizontal component of the force balance, we actually calculated the tension force, which was the required unknown force. So now let's move to the next type of the problem. So until now we will be doing the force balance analysis, or we will be solving the problems in the Cartesian coordinates where we have given x and y coordinate system, and we define the force in those x and y component, and we calculate the unknown quantities. But now we will be doing problems in the polar coordinates or in the curvilinear coordinate, where we actually need to define the component of force in the polar coordinates like r, theta, or in the curvilinear coordinates like Fn, which is normal force, or Ft, which is the tangential force. So for that we need to actually calculate the acceleration in the tangential and in the normal direction. So this is a problem where we actually try to calculate the force in the polar coordinates, and in the previous class we actually defined the velocity and the acceleration in the polar coordinates. So just to recap, the acceleration in the arc direction is r double dot minus r theta dot square, and in the theta direction it was r theta double dot plus 2r dot and theta dot. So these are the component of acceleration we need to plug into the Newton's second law, and then we can connect the force, which is a dynamic quantity, with the kinematic quantities like velocity or acceleration and so on. So in this question we need to determine the magnitude of resultant force acting on a 5 kg particle at the instant time t equal 2 seconds. When the particle is moving along a horizontal path defined by the equation 2t plus 10 meter and theta, which is 1.5 t square minus 6t rad, and here t is a time in seconds. So we need to determine the resultant force, which is given by Fr square plus F theta square, and my Fr will be from the Newton's second law, it can be given as MAR, and F theta will be MA theta. So basically in this question we need to figure out this acceleration first. Once we figure out this component of this acceleration, we can easily form these forces and then the reaction force. And to find the relation of this component of acceleration, we can see that it is given in terms of r double dot, theta double dot, r dot and theta dot and so on. So basically we need to differentiate these quantity in order to get r dot, r double dot, theta dot and theta double dot. So my r is 2t plus 10. So my r dot will be 2. So here dot means I am taking the derivative with respect to time. My r double dot will be 0. Similarly, My theta is 1.5 t square minus 6t. So my theta dot will be 3t minus 6, and my theta double dot is 3. So now we need to calculate these quantities at time equal 2 seconds, because we need to find the force at time equal 2 seconds. So in other words, we need to find the acceleration at this time. So all the quantities like r double dot, theta double dot, r dot, theta dot, we need to calculate these quantities at a given time, which is 2 seconds. So my r at time 2 will be 4 plus 10, which is 14. My r dot is 2, which is constant, and my r dot is 0. And in the same way, my theta at time equal to will be 0, and my theta double dot is constant, which is 3. So my radial component of acceleration will be r double dot minus r theta dot square. So this I am finding at time t equal to 2. So my r double dot is 0 minus my r is 14 and theta dot is 0. So basically my radial component of acceleration is 0, which means that my radial component of force is 0. The theta component of acceleration will be r theta double dot plus 2r dot theta dot. So my r is 14, theta double dot is 3, my r dot is 2 and theta dot is 0. So my a theta will be 42. Then my theta component of f will be m a theta. My mass is 5 kg. So my force will be 210 Newton. So if I calculate the resultant force, it will be equal to f theta, because this is 0. So my resultant force will be 210 Newton. So just to recap, here we have given the expression of r and theta, and we need to find the resultant force. So in order to find the resultant force, first we need to figure out the component of force, which is fr and f theta. And in order to calculate the fr, we need to calculate the component of acceleration, because from the Newton's second law, these are directly proportional to each other. And a are given by r dot minus r theta dot square, and the a theta is given by this expression, which is r theta double dot plus 2r dot theta dot. And we have already given r and theta. So by differentiate these quantities with respect to time, we can actually calculate r dot, r double dot, theta dot, and theta double dot. And at time t equal to 2 seconds, we actually plug the quantities in this expression. So once we get this acceleration at time equal to 2 seconds, we actually got this component of force. We found that Fr is 0 and F theta was 210. And then we plug this component of force here to get the resultant force. So in this case, since Fr is 0, my F will be equal to F theta. So any doubt in this problem? So we can move to the next question. So before solving the fourth question, we will solve fifth question and then we will come back to fourth. So in this question, we have the smooth particle which has a mass of 80 gram. It is attached to an elastic cord extending from O to P, and due to the slotted arm guide moves along the horizontal circular path, which is given by R equals 0.8 sin theta. If the cord has a stiffness K, which is 30 Newton per meter, and an unstretched length of 0.25 meter, determine the force of the guide on the particle when theta equals 60 degree. The guide has a constant angular velocity of 5 theta dot, which is 5 rad per second. So just to recap again, in what we are doing, we are actually using the second law of motion here to calculate the unknown quantities. So in the previous weeks, we actually started with a static problem where we actually found the unknown quantities of force. We did the force balance analysis and we actually tried to find the unknown quantity of a force. And then we moved to the kinematics problem where we have given the quantities like displacement, velocity and acceleration, and we define the relation between these quantities, and we actually found these quantities like velocity at some specific time or acceleration at some specific time. Now what we are doing here, we are actually combining this kinematics with the dynamic part where we need to calculate the force, normal reaction or the frictional force. We are actually combining these two parts by using Newton's second law. The difference here is here the system is not in the equilibrium. So in the static case, our system was in equilibrium, and that's why the summation of all force went to 0, and by doing the summation of force we actually able to calculate the unknown quantities. Here the summation of all the force will not be a 0, it will be equal to mass multiplied by acceleration from second law of Newton. So once we actually define a connection between the force, which is a dynamic quantity, and the acceleration, which is a kinematic quantity, we actually try to solve for two kind of problem. In the first part, what we have unknown quantities, unknown kinematic quantities, which is velocity, acceleration, and so on. So these are known, and we try to calculate the force, which are unknown. And in the second class of problem, the forces are known. We have given the external force or the frictional force, and we are try to found the kinematical quantity, which is velocity and acceleration, which are unknown. So in the previous problem, the question number 1 and 2, we have done the similar. We actually use this concept to found the unknowns. It can be kinematic quantities like velocity, acceleration, or could be a dynamic one, which is force. So in the previous question, we actually tried to solve in the Cartesian coordinates, where we have given the force component in terms of x, fx, and fy, or the acceleration component, which is given in terms of ax and ay. Now we are actually trying to do the same thing in the polar coordinates. So our ultimate aim is to do the force balance analysis here. Because we need to find the force on the particle here. So that can be found by doing the force balance analysis. And we know that the force can be written in terms of mass into acceleration. So in order to do the force balance analysis, first we need to figure out this acceleration. And to figure out this acceleration, we will be using the equation that we learned in the kinematics, where we actually made a link between displacement, velocity and acceleration by using these equations. So here in the polar coordinates, we have given r, which is 0.8 sine theta. We have given theta dot, which is 5 rad per second. So we can find the acceleration by taking the derivative of this, which is r dot 0.8 cos theta theta dot. And again, if we take the derivative, we will get r double dot minus 0.8 sine theta. So now I will be using the summation rule. So first I will take the derivative of this sine theta, theta dot plus 0.8 cos theta. Now I will be taking the derivative of this theta double dot. And here, since theta dot is 5, which is constant, my theta double dot is 0. And we have given the theta, which is 60 degree. So my r at theta 60 will be 0.8 sine 60 which is 0.692. My r dot at theta 60 will be 0.8 cos 60, and this theta dot is this 5. Which is 2. My r double dot is theta equals 60 minus 0.8 sine 60, theta dot is 5, and my theta double dot is 0, so this will be 0. So this will be minus 3.464. So just to recollect from the previous class, my AR is r double dot minus theta dot. So my AR will be minus 3.464. My R is 0.692. And my theta dot square is 5 square. my AR will be minus 20.94, and the theta component of A will be R theta double dot plus 2R dot theta dot. So this is 0. Theta double dot is 0, so it will be 2R dot theta dot, which is 2 multiply 5, which is 20. So my A theta is 20. So now we figure out the acceleration in both direction, AR and A theta. Now we can do the force balance analysis for this particle, and we can write the forces in terms of a Newton's second law. And after we do the force balance analysis, we can actually calculate the unknown force. So this is my particle, and let's say this is R direction, this is theta direction. So here this is my R direction here, and theta is moving here, so my theta is this direction. This is my theta direction. And let's say this is my normal reaction force, and this is the force which is acting here. Which is F. And my coordinate system here is already given. So in the radial direction, if I do the force balance, then I will have summation of forces equals to mass into acceleration in the radial direction. In the radial direction, the contribution to the force coming from the, and there is again another force is there, which is due to this spring K. So this will act here, Fs, and my Fs in the previous lectures we saw that it is K minus difference of a distance. Here it is difference of R. So my Fs is 30, which is K, and the difference of R is difference between stretch and unstretched one. So this is my R, which is total distance, minus the unstretched length 0.25, which is given in the question here. So my force due to the spring will be .24 Newton. So this is actually exerting in this direction. So now we have two forces in the radial direction. It will be minus Fs plus n cos theta equals n AR. So it will be minus 13.24 plus n cos 30 equals m, which is 80 grams, so it is 0.08 AR, and my AR is minus 20.94. So from this equation we can actually calculate this normal reaction. So it is actually 13.3 Newton. Then we will do the force balance analysis in this theta hat direction. And the forces contribution to the force coming from this normal reaction as well as the force we need to found. So the normal reaction we found is 13.3 Newton sine 30, mass is 0.08, and this is theta. A theta was 20. So my unknown force will be 8.25 Newton. So this is my unknown force. So just to recap, here we have given the smooth particle of 80 gram, and we have given how the particle actually traces the path, and it is given in terms of r, which is equal to 0.8 sin theta. We have also given information about the force due to the spring, and we have given the stiffness of the spring, and we have given the angular velocity, which is 5 feet per second, and the angular displacement, which is 60 in degrees. So now we need to calculate the external unknown force F. So as usual, we will be using the second law of motion, where we actually connect the force with the acceleration. And in order to do the force balance analysis, first we need to define the nature of the acceleration. And in the question we have already given r in terms of theta. So from this expression and from the given theta dot, which is 5, we actually found the acceleration in terms of AR and A theta. These are the components of the acceleration here, polar components of the acceleration. Once we get this acceleration, we did the force balance analysis in the both direction, the radial as well as in the theta direction. And after doing this force balance analysis, we actually calculate the unknown force. So until now you can see the approach is pretty much same in every question. So you have to do the force balance analysis, but before that you need to figure out the acceleration. And in the question, whether it is Cartesian problem or a curvilinear or in the polar coordinates, there will be some information which will be given about the distance, displacement, or the angular distance and so on. From this information you can actually find out the acceleration or the component of acceleration, and then once you get the acceleration you can actually use the Newton's second law to find the unknown force. So now let's move to the fourth question here. So even in the fourth question the concept is pretty much same. It's just mathematically more evolving. So here we have given the particle which has a mass of 0.5 kg and is confined to move along the smooth horizontal slot due to the rotation of the arm OA. Determine the force of the rod on the particle and the normal force of the slot on the particle when theta equals 30 degree. The rod is rotating with the constant angular velocity theta dot, which is 2 rad per second. Assume the particle contact only one side of the slot at any instant. So here we have given theta dot, which is 2 rad per second, which means the theta dot is 2 rad per second, which means if you take the derivative of this theta dot with respect to time, the theta double dot will be 0 because theta dot is a constant. And from the figure you can see that if this is the radial distance r and you have given the theta, and also you have given the vertical distance 0.5. So you can write cos theta equals to 0.5 by r. So you can write r as 0.5 by cos theta, which is 0.5 sec theta. So in the previous problem we have already given the expression of r. So as I said, the procedure is same. So here we need to calculate the force, and to calculate the force we will be using the Newton's second law, which is F equals ma. And if you want to do the force balance analysis, first you need to figure out the acceleration. So here also we need to figure out the acceleration, and to form the acceleration you have to deduce some unknown kinematic quantities like distance or velocity. You will already know the distance and velocity, then you can integrate these quantities or differentiate these quantities to get the acceleration and or the component of acceleration. So in the previous question we already given the velocity, which is a function of distance, and we also saw some question where we have given velocity as a function of time. We can integrate or differentiate this expression to calculate the unknown acceleration or the expression of acceleration. And once we get this acceleration, we can use the second law of motion to actually calculate the unknown force. So in this question, this is my expression of r in terms of theta. So now if I differentiate this expression, I will get r dot. And if I again differentiate this function, I will get r double dot, which required to calculate the component of acceleration in the polar coordinates. So let me first write the component of acceleration. So these expressions we already looked in previous class. And you can see that in order to calculate AR and A theta, we need to figure out R double dot and R dot. Also theta double dot and theta dot. So we have already given theta dot as 2, which means it's a constant, and if you take the derivative of it, you will get theta double dot, which is 0. And you have R, which is 0.5 sec theta. If you took the derivative of it, you will have R dot 0.5 sec theta tan theta theta dot. And if you take the double derivative of it, you will have R double dot So I will be using a chain rule here. So it will be sec theta tan theta tan theta dot plus sec theta sec square theta theta dot, and which is combinedly multiplied by theta dot plus sec theta tan theta double dot. So I can simplify writing this expression as 0.5 sec theta tan square theta dot plus sec cube theta dot square plus sec theta tan theta double dot. And you need to find the force at theta 30 degree. So R is 0.5 sec 30, which will give you 0.577 meter. Your R dot at theta equals 30. And this is multiplied by theta dot, which is multiplied by 2, which is 2 actually. So your R dot will be 0.666, and the R double dot will be 0.5 sec 30 tan square 30 multiplied by theta dot, which is 2, plus sec cube 30, and this theta dot is 0, so this term will be 0. your R double dot will be 3.42 per second square. So we identify R double dot, R dot, and R. And now we can plug these values in the component of acceleration here. So the acceleration at theta equals 30. The radial direction will be R double dot minus R theta dot square, which is 3.42 by R is 0.5774. My AR is 1.112 meter per second square, and the theta component will be R theta double dot plus 2R dot theta dot. So this is 0 because theta double dot is 0, so it will be 2 multiply my R dot is 0.66 and theta dot is 2. So here it is 2.66. So now we got the component of acceleration in the radial as well as in theta direction. So we can use the Newton's second law for both the components. So first we will be doing the force balance analysis in the radial direction. So for that, here let's make a free body diagram. So this is my radial direction and this is my theta direction. This is my weight here and this is my normal reaction. So just copy this figure. This is theta direction, this is radial direction, and this is will be my weight. And this is my normal reaction. So my radial component of force will be and cos 30 the weight is given as 0.5 kg. Equals ME. My M is 0.5 and my AR is 1.112. And my mg is 0.5 multiplied by 9.81. So from this we can actually calculate the normal reaction N. My normal force is 5.54 Newton. So we need to calculate the force in the radial direction. Here it will be F plus 0.5, 9.81 sine 30 minus, this is my n, which is acting in the theta direction, 5.54 sine theta, plus NA, my n is 0.5 and A theta is this, 2.66. So here my unknown force is 1.78. So just to recap here, the procedure is similar that we have seen so far. So we need to find the force, some external force which is acting in this direction, the theta direction here. And we need to find this force. And in order to find the force, we need to use the Newton's equation, which is given by F equals ma. And in order to use this equation, you should know about this acceleration. So first you need to find the acceleration here, which is ar and a theta. And to find this, you need some input from the kinematics, like the distance or the velocity here. So in the equation you have given this distance r, and also you have given this vertical distance, which is 0.5 meter. And you have given theta also. So you actually write r in terms of 0.5 by cos theta, which is 0.5 sec theta. So this is your r. So once you write down r, you actually derive its velocity and as well as its acceleration. You also calculate. You have also been given theta dot, and you find theta double dot as well. So by using these variables, you actually found the component of this acceleration. Now once you get this acceleration, you can able to use the Newton's second law, where you connect the dynamic quantities like force with some kinematic quantity like acceleration. So once you got this acceleration here from here, then now you do the force balance analysis in both the directions. So when we did the radial direction here, we actually found the normal reaction force, and when we did in the theta direction, we actually found out the force in the theta direction, which is this. Here this is my theta direction and this is my radial direction. So any doubt here? So the procedure is similar in all the question, it is just in a different coordinate system. So let's move to the next question. So here we have the horizontal dot OA rotates about a vertical shaft according to the relation theta dot equals tan t. And here theta dot and t is expressed in rad per second and second respectively. Here a 250 gram collar B held by a cord with a breaking strength of 18 Newton. Neglecting the friction, determine immediately after the cord breaks relative acceleration of the collar with respect to the rod and the magnitude of the horizontal force exerted on the collar by the rod. So we have given theta dot, which is tan t. So if I take the derivative of this with respect to time, I will get theta double dot, which is tan. Now here the r double dot is 0 because the r is constant 0.5. And here from if you look from this top view, we have this collar and there is a tension force here and there is a transverse force. F theta. So this is my theta direction and this is my r direction. And here I have inertial force which is acting in this direction. And before the cable breaks, I can do the force balance analysis. And my ER is r double dot minus r theta dot square. So in the r direction we have this tension as well as we have this inertial force. So it will be so the inertial force will have some acceleration and it is given at the right hand side. And then I can find the theta dot, which is the acceleration velocity. Now this quantity is 0, so we will have T by mr. and this we will get 144. So my theta dot square will be 144. So my theta dot will be 12 rad per second. Now, what if the collar breaks? If the collar breaks, then the force in the other direction will be 0, which means that MAR equals to 0. Because the collar is free to move in the art direction, so it will be M R double dot minus R theta dot square equals to 0. So R double dot will be R theta dot square. So my R double dot will be here is 0.5. So it will be 72 meter per second square. So this is the acceleration that collar will attain when it moves in the other direction. After cable breaks, it will just move in the other direction after the cable break with this acceleration. Now, in order to calculate the transverse force, we have theta, MA theta, which is M R theta dot double dot 2R dot theta dot. So it will be 0.25 multiplied by R 0.5. My theta double dot is 10 plus 2. My R dot is 0 because it is fixed. My R is 0.5. So my R dot and R double dot will be 0. So it is 0. So it will be 0.25 multiplied by 5. So it is 1.25 Newton. So this is my force in the theta direction. So just to recap, we need to find the force and the acceleration of a collar which is moving after there is a breakage of the cable. So after the breakage of the cable, the force in the radial direction will be 0, which means F R, which was equal to MAR. Since it is a 0 force, I will get MAR equal to 0, and from this I can actually calculate the acceleration, which is 72 meter per second square. Now, in order to calculate the transverse component of the force, I here can calculate the F theta, which is given in terms of MA theta. So first I calculate the A theta and then the force F theta. So now we come to the question which actually come from the rigid body dynamics. So in the rigid body dynamics, what happens that you have given a body and you are interested in calculating the angular rotation of the body. Suppose you have given the angular acceleration or angular velocity. From that expression, you are interested in calculating the torque or the rate of change of angular momentum. And hello. Now, can you mute your mic? Thank you. So basically in this class of problem, we will be more interested in the calculating the movement in a rigid body, which can be defined in terms of a rate of change of angular momentum or due to the angular acceleration. So in the previous class, we actually looked some relations. For example, we actually looked some relation like v equals to r theta dot, my normal component of acceleration which was v square by r, or r theta dot square, or v theta dot. My tangential acceleration was v dot, which is r theta double dot. So if a body is rotating in a plane, then I can define omega, which is d theta by dt, which is my theta dot, and the angular acceleration, which is omega dot or theta double dot. Now I can write their own kinematics equation, like omega equals omega naught plus alpha t, omega square, omega naught square plus 2 alpha, theta minus theta naught, and theta equals theta naught plus omega naught t plus 1 by 2 alpha t square. So these are the expression that we actually saw in the previous class. So now our objective is to write this expression in terms of a vector quantity, which will be helpful in solving the three-dimensional problem. So let's say I have given a point O, and there is a angular velocity. There is a point A which is moving or rotating. Now this is your component of acceleration in a normal direction, and here is the acceleration in the tangential direction. Now your velocity can be written as omega r, or your omega is theta dot, so it will be theta dot r, which is exactly this relation. So all this relation you can see, these are given in the form of scalar components. In the vector component, you can actually define the relation between velocity, angular velocity, and radial displacement r by using the cross product. So your velocity can be given as omega cross r, and your acceleration is rate of change of velocity, which is omega cross r. The component of this expression is, you will get r omega or r theta dot. Here if I take the derivative to find the acceleration, I can use the summation rule. So it will be omega into r dot plus omega dot cross r. So my r dot is just this velocity, right? R dot represents the velocity. So, and we know this velocity can be represented by omega cross r plus omega dot cross r. So I can write this expression as omega cross v or omega cross r, and this you can see is the angular acceleration alpha plus angular acceleration cross r. So this is your acceleration in the vector form that can be useful in the higher dimensional geometry. This is your velocity vector and this is your acceleration vector. So this part is your tangential acceleration, this one, and this part is your normal acceleration, which is this one.
Hello. Now is it audible now? Hello.
I mean, is it more clear? Okay. So until now we actually connect the dynamic quantity like force with the kinematic quantity like velocity, acceleration, so on by using the Newton's second law. But now on, we will be doing the same thing for the rotational motion. So for the translational motion, you have Newton's second law, which is F equals ma. Now for the rotational movement, we are more interested in finding in moment, which can be given as rate of change of angular momentum. So your resultant movement equal to rate of change of angular momentum. So your angular momentum can be given as your position vector. Let's say it's a rho multiplied by mass into rho dot. So here let's say you have a body and G is your center of mass, and here you have a mass of this particle, which is mi. This is your x-axis, this is your y-axis. And here is your acceleration, and this is your angular acceleration and angular velocity. This is your vector rho I. It's a position vector from the center of mass to this elementary particle. And from this calculations here, we saw that my velocity can be written as omega cross rho vector. So my momentum will be rho vector multiplied by mass, it's a cross product with mass, omega cross with rho. So this is the expression for the angular momentum. Now we can see this. The component of this will be omega rho, and here it is rho. So the component of angular momentum will be omega rho square. So basically, if you consider the mass, the component of angular momentum will be m rho square omega, which is summation here, which is omega summation mass rho square. And this quantity, you already know this quantity is actually your rotational moment of inertia, which means your angular momentum will be omega multiplied by moment of inertia. And here you can see that the net movement is the rate of change of angular momentum, and angular momentum is angular velocity multiplied by rotational inertia. So it is d by dt omega I. So if I fix the rotational moment of inertia in time, so I will get I omega dot. So this is, or I can write this as I alpha, because omega dot is acceleration, angular acceleration. So omega dot can be written as alpha. So this I alpha is the summation of all moments. So my summation of all moment will be given by I alpha. It is equivalent to the summation of all forces, which is equal to ma. So this is valid for lean translational motion, and this is valid for rotational motion. So earlier until now we have looked the problems where we use this relation. Now we will be looking problems where we will be using this or the combination of these two. And also let's say you have given some arbitrary point. Let's say here you have given P, and there is a position vector rho bar. Then for this case your movement at that point P will be given as rate of change of angular momentum at your center of mass plus rho bar cross with acceleration at that point P, which is I alpha, that we have seen that this is I alpha plus m a d. D is the position vector between that point P and the center of mass. So this is your vector form, and this is your scalar form. This is when you have given some arbitrary point P in the body. Hello? Yeah.
Actually, I had some doubts, very basic doubts, and there is only 15 minutes left. So, can I ask?
Yeah, sure. Yeah, sure.
They're quite basic doubts.
Yeah, go ahead.
The thing is what is the we say that a body in motion and a body in a state of rest, they are same, like by Newton's first law.
Body in motion and body at state of rest is
body in uniform motion. Sorry, uniform motion and a body in rest, they are equivalent.
Okay. So I think you are talking about the initial frame of reference. So what happens that, for example, the forces actually depend on this acceleration. So according to the Newton's law, the force is equal to the mass multiplied by acceleration. So what happens that when people actually try to validate this expression, they actually calculate the ratio of force by acceleration, and this come out to be a constant. Now what happens to perform this motion? You need to choose some frame of reference. So usually we choose inertial frame of reference. So in that inertial frame of reference, the body is at rest. I mean, body is not at rest. You actually study the body which is moving, and the frame of reference, this frame of reference is at rest. So basically, suppose what happens, you want to observe the ball falling. Okay. Now you are actually recording the ball falling. So the environment around this ball is not moving at all. So this is the inertial frame of reference. Since it is not moving, you can actually calculate the acceleration. And this is the absolute value of acceleration. Now, take the another example where your this frame of reference moving at a constant speed. It is moving at a constant. Your frame of reference moving at a constant speed, which means the acceleration of your frame of reference is zero. Which means that if you calculate the acceleration of this body, you will again get the absolute acceleration because it's moving with a constant velocity, which means the acceleration of the frame is zero, which means you can able to calculate the acceleration of this particle in an absolute value. You can actually get the correct value of acceleration. But now let's say your frame is moving with some acceleration a1 and your body which you are studying moving with some acceleration a. Now when you calculate this acceleration a, you will get different results because your frame of reference is also moving with some acceleration. For example, let's say Earth, which is moving with some acceleration, and now you are actually calculating the acceleration of this body. You will find that it is not equal to this constant. It is a little different from this constant. So now here you need to consider this acceleration. In order to get the same constant, you need to take this relative acceleration into account. And that's why we say that if the frame of reference which is at rest or if it is moving at a constant velocity, it is equivalent because in both the cases the acceleration of the frame is zero. Did you got my point?
And one thing is like, yeah, sure, very clear. And the thing is like this ratio, we call this ratio as mass.
Yeah. So this ratio is actually measure the inertia of the body. So in the translation, this inertia is mass. But in the rotational motion, we see that this actually a rotational moment of inertia. Whereas in translation motion, that quantity is mass. So these are the constants. So this is for rotational motion, and this is
my question is like mass is something we can call as quantification of inertia.
Yeah, exactly. Yes. It is a quantification of inertia in the translation motion. In a rotational motion, it will be different. It will be a moment of inertia. But in a translation motion, mass will be the quantification of inertia.
Okay, and if just one example, like if a vehicle is moving like with a constant velocity, let's say 30 meter per second, and then at that time the forces are balanced because it is moving in a uniform velocity. So if there is some friction and there is some driving force, they are balanced. That's why it is moving in 30 meter per second. Now there is a same vehicle, another vehicle which is moving with 60 meter per second, and now also the forces are balanced, right? So in both the cases, forces are balanced, right? So but we say that more energy is consumed in the vehicle which is moving with 60 meter per second, right? More power is required to move at 60 meter per second, right?
Okay.
Yeah, so what is the driving thing? Like how it comes to, like what is the drive? Like we has a perception that something if we are driving something, there is something force behind it. In both those cases the forces is equal, but each forces is balanced, net forces are zero, like in 30 meter per second and in 60 meter per second. But in the 60 meter per second the energy consumption is more, or we can say power consumption is more. So what is the cause behind that? If force is not the cause, then what is the cause?
There must be some component of the force because if let's say your object is moving in some horizontal direction, there will be a friction force, there will be a normal reaction, there will be a weight, then there will be a force due to inertia. Now, the summation of all these forces will be maybe equal, but there might be some this specific force, either this inertial force or this normal force, weight or Fs, which will be imbalanced, which will be different from the other one in case if you increase the velocity. So that I think that will
Not
make
increase when it is moving at uniform velocity. No, we have to change the state. Then we need a force. That's okay, because that
Yeah.
is by first law we say that to change the state of motion we need some force, external force. But we are in a uniform motion at 30 meter per second. So, and at that time, what is the driving force? And at 60 meter per second, we are consuming more energy. But at that time also forces are balanced. So what is the cause behind that? Like,
so
So
it
it
is,
is,
yeah.
difficult to sometimes write this.
No, it is consuming more energy because of the kinetic energy. Because if the body is moving, it has some kinetic energy, and the kinetic energy is 1 by mv square. Now you say the velocity is constant in both the cases. In first case it is 30, and in second case it is 60. So here the kinematic energy in the 60 case will be higher because the kinetic energy proportional to v square, which means if you increase your v, your kinetic energy will be more. That's why you require more power to move a mass m with to a higher velocity. So you are
are
Yeah,
more
mathematically we can say that.
yeah.
But cause behind that is what I'm interested in. Like, what is the cause? Like,
I
I think
there is no.
yeah,
so I think the
inertia force here will be, I think it will be much higher than the previous case. The
The
force will be different.
Okay. Hmm.
Because
So
it is
this
mo-
inertia.
yeah.
Yeah, that is my second part of the question. Actually, when you start discussing about kinetic energy, actually we say that momentum. We talk about momentum. So inertia is the like is something which we need to change the state of motion. But actually, it is momentum which is we need to change the state of motion,
No,
because
no. Inertia actually restrict you to change the motion. So
So
it is actually retarding you to move. Inertia is actually restricting you to move ahead. Momentum is actually moving you in the specific direction. Inertia is doing the opposite thing. It is trying to stop you.
yeah. But if some body has more momentum,
Yeah.
like it is mass and multiplied by velocity, has more momentum, then we need more force to change its state.
Well, if the body has more momentum, let's say it's a
so
difference between
Yeah.
velocity, then it yeah,
yeah,
it will require more force. Yeah, it will exert more force. Yeah.
Yeah, so this is the point where confusion arises, because momentum may be same, but if of a particular momentum inertia is same, because same body, same mass. If we have one body, it has a particular mass, so it has a inertia is sometimes I can say property of that particular body, so it is same. But if we increase the velocity, we need more force to change the state of motion, but the inertia is same because mass is same.
Yeah,
yeah,
mass is same. So here see the forces actually depend on the difference between the velocity, and the
and the
momentum
momentum
is just
just
the
the
mass
mass
multiplied by
multiplied by
velocity.
velocity.
So what
So what
happens if you apply 60?
60?
If your
If your
velocity is 60, your momentum will be greater than when your
when your
velocity is 30.
30.
And here
And
the
here
same
the
thing
same thing
happens
happens
here.
here.
The
The
force
force
at
at
60 will be greater than the force at 30 because your difference between, let's say, your initial velocity is 0. So this is 0. But your final velocity is here is either 30 or 60. So in both the cases you can see that again
again
your
your
force
force
and
and
momentum will
momentum
be
will be
greater
greater
than
than
when your
when your
velocity is
velocity is
60.
60.
Your
Your
kinetic
kinetic
energy is
energy is
also
also
greater
greater
when the
when the
velocity is
velocity is
60.
60.
So
So
this is
this
the
is the
force.
Yeah,
So this is
maybe
the
by the next, maybe,
so
so
this is
this is
only
only
I'm
I'm
talking
talking
about the
about the
inertial
inertial
force,
force,
and this
and
is
this
the
is the
momentum.
momentum.
yeah. So actually, we talk about conservation of momentum. Like why we need a conservation? Like how, why momentum is conserved?
Because
Because
let's
let's
say
say
you have a
you have a
body
body
here
here
and
and
another
another
body
body
here
here
which is
which is
moving
moving
at
at
some
some
certain
certain
direction
direction
and
and
at
at
some
some
and
and
also
also
with
with
some
some
velocity v.
velocity v.
This
This
body is
body is
at
at
rest.
rest.
What
What
happens with
happens with
what do you
what do you
mean by
mean
the
by the
conservation of
conservation of
momentum?
momentum?
It is
It is
actually
actually
what
what
happens
happens
when
when
this
this
body
body
hit
hit
this
this
body,
body,
it
it
actually
actually
transfers the
transfers the
momentum to
momentum to
this
this
body,
body,
which
which
means
means
that
that
let's
let's
say
say
it
it
can
can
able to
able to
transfer
transfer
the
the
all
all
momentum.
momentum.
So
So
when
when
this
this
body
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 1
one
will
will
hit
hit
body
body
2,
two,
the
the
body
body
1
one
will become will
will
come
come
at
at
rest
rest
and
and
body
body
2
two
will
will
start
start
moving at
moving
the
at the
same
same
velocity
velocity
v
v,
because it
because it
transfers
transfers
the
the
all of
all of
its
its
momentum to
momentum
the
to the
body
body
2.
two.
So you
So
can
you can
see the
see the
momentum
momentum
can be
can be
transferred
transferred
from
from
one
one
body to
body
the
to the
another
another
body
body
when it
when it
hits.
hits.
Yeah,
So
and yeah. So yeah, that I understand. But actually, the problem is there is no. I don't understand the cause why it is happening. Like it, my mathematical sense, I can, like we can solve the issue problems, and we can get to the solutions that okay, momentum is conserved, so we can how much is, if depending upon the elasticity, like how much velocities are exchanged and all those things. But the cause behind those things are unclear till now, like how it is happening.
So
So
basically, the
basically, the
force
force
is
is
rate of
rate of
change of
change of
momentum,
momentum.
and
And
according to
according
the
to the
Newton's
Newton's
law,
law,
you
you
need
need
a
a
external
external
force
force
in
in
order to
order to
move,
move.
and
And
force is
force is
also
also,
you can
you can
say
say
it's a
it's a
rate of
rate of
change of
change of
momentum.
momentum.
So
So
what is
what is
happening?
happening?
So
So
this
this
body
body
which
which
is
is
at
at
rest,
rest,
it
it
does
does
not
not
experience
experience
any
any
force,
force.
and
And
according to the
according to the
Newton's law,
Newton's law,
if
if
anybody
anybody
don't
don't
experience any
experience any
force, it
force,
will
it will
always
always
remains at
remains at
rest.
rest.
Now what
Now what
happens that
happens that
another
another
body
body
came
came
and it
and it
hit the
hit the
second
second
body.
body.
Now
Now
what
what
happened? There is
happens?
a
There is a
transfer of
transfer of
momentum,
momentum,
and the
and the
transfer of
transfer of
momentum
momentum
is
is
associated with
associated
the
with the
force. It
force.
is
It is
actually a
actually a
force,
force,
which
which
means
means
when it
when it
transfers the
transfers the
momentum,
momentum,
the
the
body
body
1
one
is
is
actually
actually
applying a
applying a
force to
force
the
to the
body
body
2,
too.
and due
And
to
due to
this
this
force
force,
only
only
this
this
body to
body to
start
start
moving,
moving.
because
Because
according to
according
the
to the
Newton's law,
Newton's law,
you
you
need an
need an
external
external
force to
force to
move,
move.
and the
And the
force
force
can be
can be
represented by
represented by
change of
change of
momentum,
momentum,
which
which
is
is
imparting by
imparting by
body
body
1
one
to
to
body
body
2,
two.
and
And
due to
due
the
to the
rate of
rate of
change of
change of
momentum,
momentum,
there
there
will be
will
a
be a
force
force
from
from
body
body
1 to
one to
body
body
2,
two.
and due
And
to
due to
this
this
non-zero
non-zero
force,
force,
the
the
body
body
2
two
now
now
start
start
moving.
moving.
Yeah, yeah, yeah. Now I understand. But the last part of this thing is like, okay, so I need a conservation of momentum and two bodies. Then
Yeah.
by separately, sometimes we need conservation of kinetic energy also, like total energy maybe.
Yeah.
But I, if I just remove the potential energy part, we need, like momentum is conserved now. Everything is okay. Why we need extra one thing, that and then energy should be conserved. Sometimes it happens that and momentum is conserved, but kinetic energy is not conserved.
Well,
Well,
in
in
that
that
case,
case,
what
what
happens
happens
that there
that
is
there
a
is a
some
some
amount of
amount of
energy
energy
which
which
can be
can be
dissipated
dissipated
in
in
terms
terms
of
of
heat.
heat.
But
But
usually
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 what we
what we
consider,
consider,
especially at
especially
the
at
undergraduate
undergraduate
level
level
courses,
courses,
that
that
the
the
kinetic
kinetic
energy
energy
remains
remains
conserved,
conserved
because
because
it
it
can
can
transfer
transfer
all of
all
its
of its
energy to
energy
the
to the
another
another
body, and
body, and
it is
it is
keep
keep
doing
doing
that.
that.
If the
If the
kinetic
kinetic
energy is
energy is
not
not
conserved,
conserved,
then
then
what
what
happens?
happens?
Some
Some
amount of
amount of
energy
energy
dissipated
dissipated
into
into
heat,
heat,
which is
which is
usually
usually
very
very
low in
low in
amount, and
amount,
so
and
on.
so on.
Now,
Now,
coming
coming
back to
back to
your
your
question,
question,
that
that
I
I
mean,
mean,
why we
why we
need
need
conservation of
conservation of
kinetic
kinetic
energy
energy
also.
also.
So
So
there are
there are
two
two
way I
way
can
I can
explain
explain
this.
this.
The
The
first is
first
in
is
more
in more
general.
general.
Now,
Now,
in the
in the
classical
classical
mechanics,
mechanics,
actually
actually
we do
we
the
do the
force
force
balance
balance
analysis,
analysis,
and
and
we
we
use
use
Newton's
Newton's
law
law
in
in
order to
order to
analyze the
analyze the
system. So
system.
this
So
is
this
one
is
of
one
the
of the
mechanism
mechanism
how
how
we
we
study
study
the
the
problems in the classical mechanics. There is another way also. in the another way, what happens, we write down the energy equation, and then we write down all the components of energy like kinetic energy, potential energy, and we say that okay, now we follow the conservation of energy. From energy equation, you can actually get the Newtonian equation, or you can actually get the momentum equation. So this is another way. So in this way, you are actually know about the energy, and you are actually getting the momentum equation. So people also approach in this way. So this is one of the reasons why people do conservation of energy. The second reason is what happens that if you do the conservation of momentum and you do the conservation of energy, so you can write down the multiple equations. So you can write down at least two equations here and at least one equation here. So you can solve for more unknowns. So let's say you have a three unknowns. You can write down the conservation of momentum and conservation of energy. So you can solve three unknown quantities. If you don't consider this, then you can only solve two unknown quantities. So sometimes to solve for extra unknowns, you have to write down the conservation of energy, or you need to consider this conservation of energy equation into the account. So these are the two general reasons why usually people also care about the conservation of energy.
Okay, yeah, but in when we look into some broad equations of any system, there also we have three equations. Like first is conservation of mass, second is conservation of momentum,
Yeah.
and the third one is conservation of energy.
Yeah.
So at those places also energy and momentum and equations are separately written. But are they equivalent? Like we can drive energy from energy equation, we can drive momentum equation. Is this the case?
So basically, there is a concept which is called Lagrangian. So in what happened in the Lagrangian concept, I mean, it is pretty much not in the UG curriculum, but what happens there, if you are using Lagrangian principle, you can actually deduce the momentum equation. So there is something called action, which given in terms of Lagrangian, and some integration. So this is actually the conservation. You can write the Lagrangian in terms of conservation of kinetic and potential energy. You say action is zero, so which means your kinetic and potential everything will go to zero. And from this, you actually able to write down the equation of motion like this. So basically, you will get some theta double dot equals to gh, something like this. So this equation is your pendulum equation. Similarly, in the Cartesian coordinate, you can able to write x double dot some gx equal to 0. So this is the differential equation you can get where you define the acceleration x double dot plus some distance gx. You can solve this equation by using you can solve this differential equation. You will get x in terms of some exponential of gx or something like that. So basically, this is the way you are actually calculating from the energy principle. But that is little beyond what you study in the UG. But yeah, you can actually get the momentum equation.
Yeah.
Or
means, yeah. So basically, we can say that energy and momentum equations are equivalent.
I mean, not equivalent. See, in the previous classes, what we have done, we do the force balance analysis when the body is in equilibrium. Here, you are getting some equation to the momentum, but that is not exactly. I mean, it's not an equivalent actually. I should say.
Yeah, that is the problem actually. Even if energy, some kinetic energy is not conserved and some energy is lost in heat or something, at that time, but momentum is conserved. So like they can't be equivalent. Like there is something different. Because if energy is lost, then momentum should also not be conserved.
No, so these quantities actually are connected to each other by kinematic variables. like
like
velocity and
velocity and
acceleration.
acceleration.
So
So
if you
if you
say
say
that
that
there is a
there is a
loss in
loss
the
in the
kinetic
kinetic
energy,
energy,
which
which
means
means
the
the
change of
change of
velocity
velocity
should be
should be
different.
different.
Like
Like
your
your
final
final
velocity and
velocity and
initial
initial
velocity,
velocity,
like
like
these
these
two
two
things
things will
should be
should be
very
very
different.
different.
I
I
mean,
mean,
let's
let's
say
say
for
for
example
example
case
case
1.
one.
Here
Here
you
you
have
have a
no
no
loss
loss
in
in
the
the
energy.
energy.
So
So
there
there
will be
will
a
be a
velocity,
velocity,
final
final
velocity
velocity
minus
minus
initial
initial
velocity,
velocity,
which
which
will
will
be,
be,
let's
let's
say,
say,
your
your
del V.
del V.
Now
Now
case
case
2,
two,
where
where
you have
you have
considered
considered
some
some
losses.
losses.
Okay,
Okay,
now
now
what
what
happens?
happens?
This
This
is
is
loss,
loss.
this is
This is
no
no
loss
loss
in
in
kinetic
kinetic
energy.
energy.
Now
Now
here
here
this
this
del
del
V1
V1
will
will
not be
not be
equal to
equal to
del
del
V2,
V2,
because
because
there is
there
a
is a
loss in
loss
the
in the
kinetic
kinetic
energy,
energy,
which
which
means
means it
this
will
final
this
velocity
final
will
velocity
not
will
reach
not reach
VF1.
VF1.
Bec-
Like,
Okay,
okay,
let's say
let's say
my
my
VF1
VF1
is
is
10.
10.
If there
If
is a
there is a
loss,
loss,
my
my
VF2
VF2
will
will
reach up
reach up
to
to
8
8
or up
or
to
up to
9,
9,
but it
but
will
it will
not
not
reach up
reach
to
up to
10
10
because of
because
the
of the
loss.
loss.
So
So
this
this
delta
delta
V2 and
V2 and
delta
delta
V1 will
V1
be
will be
different.
different.
And
And
when
when
this
this
delta
delta
V1 and
V1 and
delta
delta
V2 is
V2 is
different,
different,
you
you
can
can
see
see
the
the
momentum
momentum
or the
or the
forces
forces
in these
in
two
these two
cases will
cases will
also be
also be
different.
different.
So you
So
can
you can
see the
see the
force
force
dynamic
dynamic
quantities like
quantities like
force and
force and
momentum,
momentum,
or
or
the
the
energy
energy
quantities like
quantities like
kinetic
kinetic
energy.
energy.
These are
These are
actually
actually
connected with
connected with
each
each
other
other
by
by
this
this
kinematic
kinematic
quantity,
quantity,
velocity or
velocity or
acceleration.
acceleration.
So if
So
there
if
is
there is
a
a
change of
change of
velocity,
velocity,
yeah,
yeah,
there
there
should be
should be
the
the
change.
Yeah, I understand. Like you are basically you are saying, well, there is a change, but means velocities are different, but means the momentum is conserved.
Yeah,
yeah,
Basically, momentum is conserved because the exchange of velocity is happening.
yeah,
yeah,
Like, but that is not same when there is a loss.
yeah,
yeah,
Exchange of velocity is different.
yeah.
yeah.
So energy is not conserved
No,
there,
Look,
but
yeah.
yeah,
momentum is.
No, no.
no, no.
My
My
point
point
is
is
momentum in
momentum in
this
this
case and
case,
this
in this
case is
case, is
different
different
as
as
like a
like a
energy.
energy.
So
So
conservation of
conservation of
energy in
energy
this
in this
case and
case
this
and
case
this
are
case are
different.
different.
So
So
does the
does the
momentum
momentum
conservation.
conservation
In both
in
cases
both
will be
cases will be
different
different,
because the
because the
final, which
final,
is
which
the
is
del
the del
V1, del
V1,
But
del
if
V2,
V2,
there is a loss,
yeah,
yeah,
there is a
there is a
loss.
loss.
That's
That's
why
why
del
del
1,
1,
del
del
V1
V1
not
not
equal to
equal
del
to del
V2,
V2,
and
and
that's
that's
why
why
there will
there
be
will be
a
a
change in
change in
momentum
momentum
here,
here,
which is
which is
different
different
with
with
compared to the
compared to the
case 1.
case one.
So if
So
the
if the
change of
change of
momentum is
momentum is
m1,
m1,
here
here
is
is
m2,
m2,
and here
and
it
here
is
it is
m1,
m1,
the
the
m1 is
m1 is
not
not
equal to
equal to
m2.
m2.
The
The
like that's okay. I understand that there is a difference in velocities, but still, if something is lost, then how can momentum be conserved?
because
because
you are
you are
thinking in
thinking in
terms of
terms of
energy,
energy
actually you
actually.
are
You are
thinking
thinking
that
that
okay,
okay,
there is
there is
some
some
kind of
kind of
energy
energy
lost,
loss,
but
but
now
now
how I
how I
imagine in
imagine in
terms of a
terms of a
momentum?
momentum?
You have
You
to
have to
imagine in
imagine in
terms of
terms
a
of a
rate of
rate of
change of
change of
velocity,
velocity.
because if
Because
there
if
is a
there is a
change in
change in
kinetic
kinetic
energy,
energy,
then there
then
will
there
be a
will be a
change of
change of
final
final
velocity.
velocity.
And if
And
there is
if
a
there is a
change of
change of
final
final
velocity,
velocity,
then there
then
will
there
be
will
a
be a
change in
change in
momentum
momentum
also.
also.
So
So
imagine the
imagine the
momentum
momentum
as a
as a
rate of
rate of
change of
change of
velocity.
velocity.
You
You
can
can
imagine
imagine
the
the
loss in
loss in
kinetic
kinetic
energy as
energy as
some
some
dissipation of
dissipation
heat
of
or
heat or
something,
something,
but
but
try to
try to
imagine
imagine
the
the
rate of
rate of
change of
change of
momentum
momentum
in
in
terms of
terms of
velocity
velocity
differences.
differences.
So
So
here,
here,
in
in
second
second
case,
case,
what
what
happens? The
happens? The
velocity
velocity
difference
difference
is
is
different
different
from the
from the
previous
previous
case,
case,
and
and
therefore,
therefore,
due to
due
the
to the
difference in
difference
the
in the
velocity
velocity differences,
different
different
velocity
velocity
differences,
differences,
the
the
momentum will
momentum
be
will be
different
different
from the
from the
previous
previous
case,
case,
because the
because the
final
final
velocity will
velocity
be
will be
different.
different.
VF2 is
VF2 is
different than
different than
VF1,
VF1,
so the
so the
rate of
rate of
change of
change of
momentum will
momentum
be
will be
different, right?
different, right?
Because
Because
it's
it's
a
a
final
final
velocity
velocity
minus
minus
initial
initial
velocity.
velocity.
Initial
Initial
velocity is
velocity is
same in
same in
both the
both the
case,
case,
but
but
final
final
velocity is
velocity is
different in
different in
both
both
cases,
cases,
which
which
means
means
the
the
momentum in
momentum in
both cases
both
should
cases should
also be
also be
different
different
because of
because of
different
different
subtraction subtraction of this velocity or the difference in the velocity.
Yeah, I understand, but can we see it from example? Like, if you can please assume two bodies of same mass.
Yeah.
Yeah.
So I mean, the example will say the
Two
same.
bodies of same.
So let's say it has the same mass. this body is, let's say, second body, and this is first body. This is moving with velocity v. My initial velocity is 0.
Please give some value like 10.
Hmm?
Yeah, or 10 or something. Please
Right?
give some quantity like 10 meter per second. So then I will.
Oh,
it
okay,
is
okay.
easy to understand.
Okay, let's say it's 10 meter per second. Now the momentum, let's say we evaluate two quantities. Conservation of kinetic. No, you already can imagine the energy, let's say momentum only. So here what happens? This is my case A. This is my case B. It contains loss. Okay, it contains some loss in the kinetic energy. Now, due to the loss in the kinetic energy, what happens? Its final velocity. Its final velocity, let's say, is very different. So, what happens? This body. This is the final position of this body, one. And since there is a loss in the kinetic energy, this body will start moving with some lesser velocity because there is a loss in the kinetic energy. So what happens? This will strike to the body 2 with some less velocity. Let's say it strike to a body 2 with a velocity of 9. So it started moving with 9 meter per second. But in case A, since there is no loss in the kinetic energy, when it collide, it is moving with 10 meter per second. Now you can see the momentum. Here the momentum is high, and here the momentum is pretty much low because it's proportional to 10 minus 0, and here it is proportional to 9 minus 0.
Yeah. But means in the second case, the first body strike with 9 meter per second.
Because you say there is a loss in the kinetic energy. So if there is a loss in the kinetic,
After colliding it, there will be loss.
so even let's say after colliding, there is a loss. So what happens? There is some dissipation, and it will actually it will share only some part of the momentum. It will not share this full momentum. It will share only a part of it because the remaining one get lost in energy. That means only some part of the momentum it can share. And due to that some part, it will start moving, let's say, 9 meter per second.
Yes, yes, and like in the second case, how we can say that momentum is conserved? Okay, energy is not conserved. How, like by quantity, like how we can say the initial momentum is 10 into m, and final momentum will be m into 9. But still, we say like in that case, like if there is elasticity, means E value, means coefficient of elasticity is 1, then we can say that momentum is conserved.
So if the first body will be at rest, then we cannot say the momentum is conserved. Because yeah. So if there is a, I don't think we can say the momentum is conserved.
Like if that coefficient of elasticity we found E something like a coefficient of collision or something, I still don't remember exactly the name, but if that is 1 in both the cases, then momentum we say conserved, but in the second case we say kinetic energy is not conserved. That is my actually question. So
I think in this case you cannot say the momentum is conserved in the case B. But anyway, I mean,
yeah, that's okay, but we can have such cases like maybe this is not an ideal example, but there are cases where momentum is conserved but energy is not conserved.
well, I need to think of those examples. I cannot get straight away. I need to think a little bit about these examples.
Yeah, I can And online also, I can have, there are some examples like momentum is conserved. Is conserved. Hmm. Uh, there are multiple sources. I'm not getting exactly, but there are there are examples like about this, and that there's the this is the point where confusion arises. Like one is the inertia and momentum thing, and then momentum and energy. This transition is difficult to imagine. Like if a body, like still I can imagine that thing, that if a my question at that time also was that if a body is moving with 30 meter per second and something is moving with 60 meter per second, then then from extracting more energy to move at 60 meter per second, we don't find any cause. It's just that I can say from Newton's first law that okay, if it is in a state of that 60 meter per second, forces are balanced, then it is keep moving. That is okay. But more energy is conserved. It is not like it is not taking energy. It is like if I run, if the car is moving, then it is draining out more energy from the engine. Like that is the question. You understand? Because I cannot start mechanics because of these things. The two basics confusions.
Okay.
Like how it can extract energy from engine, like if forces are balanced, everything is okay. Like and from the Newton's first law I can say that okay, forces are balanced, there is no external force, so we need not change the state of motion, so it will keep running on that particular speed. Okay, but how then, how it is taking more energy? Like if I can say okay, to balance that force in the forward direction, it continuously taking more energy, it means that energy is converting into force or something like this.
No,
No,
energy and
energy and
force,
force,
these are
these are
completely
completely
different
different
quantities.
quantities.
Force is
Force
a
is a
vector
vector
quantity and
quantity and
energy is
energy
a
is the
scalar
scalar
quantity,
quantity,
and
and
they
they
actually
actually
represent
represent
something
something
completely
completely
different
different
uh, thing
thing
in the
in the
mechanics.
mechanics.
But
But
yeah,
yeah,
there is
there
a
is a
connection.
connection.
Like
Like
both
both
quantities
quantities
depends on
depends
the
on the
kinematic
kinematic
quantities
quantities
like
like
velocity
velocity
or
or
acceleration or
acceleration or
these
these
quantities.
quantities.
So
So
it
it
just
just
we need, when
when
you do
you
the
do the
force
force
balance
balance
analysis,
analysis,
you
you
actually
actually
okay,
okay,
let's
let's
do
do
one
one
thing.
thing.
Let me
Let me
go
go
through
through
your
your
examples. Like
examples. Like
let me
let me
find
find
something if
something if
I
I
can
can
find if
find
there
if
is a
there's a
violation in
violation
the
in the
conservation of
conservation of
energy
energy
but
but
not in the
not in the
momentum.
momentum.
And
And
let's
let's
discuss
discuss
this in the
this in the
next
next
class,
class
because
Okay,
in
because
so
the
the next section,
yeah,
yeah,
because in
because in
next
next
class
class
there
I,
are like these
yeah,
two things.
yeah, in
yeah,
the
in the
next
next
class I
class I
will
will
anyway
anyway
going
going
to
to
start
start
with
with the
impulse,
impulse,
momentum,
momentum,
all
all
these
these
thing.
thing.
So
So
we can
we can
discuss all
discuss
these
all these
things in the
things in the
next
next
class then.
class then.
Yeah, sure, please. Okay,
Okay.
so in the next class, like these two things. One thing is like this car moving with the different how it is consuming, and the second thing is this, that conserve momentum is conserved but not kinetic energy.
Yeah, I
Yeah, I
mean,
mean,
see,
see,
the
Right.
second thing
second
is the
thing is the
most
most
general
general
thing,
thing
because
because
I
I
mean I
mean I
can
can
try to
try to
find
find
these
this
relation
relation
examples
examples
also.
also.
About the
About the
car
car
thing,
thing, it's
see,
see,
it's
it's
completely
completely
based on the
based on the
applications.
applications.
Like
Like
I mean,
I
I
mean
can
I can
explain these
explain these
things, but
things,
the
but
thing
the thing
is,
is
it is a
it is a
combination of
combination of
several
several
complicated
complicated
parts.
parts.
So
So
first there
first
is
there
a
is a
energy
energy
wheel generation
generation
generating in the
generating in the
IC
IC
engine.
engine.
and due
and
to
due
the
to the
generation
generation
of
of
energy in the
energy in the
IC
IC
engine, there
engine,
will
there
be a
will be a
movement of
movement
some
of some
part
part
in the
in the
engine.
engine.
That
That
part will
part will
turn
turn
movement the
movement the
shaft,
shaft,
and the
and the
shaft will
shaft will
move the
move the
wheel.
wheel.
So
So
there is
there
a
is a
long
long
chain of
chain of
complicated
complicated
parts which
parts which
are
are
arranged
arranged
with
with
each
each
other,
other,
and
and
so
so
it
it
might be
might be
little
little
difficult
difficult
to
to
explain
explain
things.
things.
But
But
yeah,
yeah,
there is
there is
a
a
energy.
energy.
It is
It is
actually
actually
the
the
energy
energy
which
which
is
is
creating in the
creating in the
IC
IC
engine,
engine,
and
and
then
then
that
that
energy will
energy will
transfer
transfer
to
to
some
some
rotational
rotational
part,
part,
and that
and that
rotational
rotational
part
part
is
is
actually
actually
transferring its
transferring its
momentum to
momentum to
the
the
shaft,
shaft,
gears,
gears,
and then
and then
gears to
gears
the
to the
shaft, and
shaft, and
shaft to
shaft
the
to the
another
another
shaft,
shaft,
and
and
then
then
that
that
shaft to
shaft
the
to the
wheel
wheel
at
at
the
the
rear
rear
wheel.
wheel.
So
So,
but
but
I
I
think that
think that
if you
if you
can able
can
to
able to
understand the
understand the
general
general
concept like
concept
your
like your
second
second
question,
question,
then you
then
can
you can
easily
easily
able
able
to
to
know the
know the
first
first
problem
problem
about the
about the
car,
car,
because
because
first
first
problem is
problem is
more
more
application
application
based. So
Yeah,
you
based. So
need
you need
but in car, like, yeah, so but in for understanding purpose, I can remove all this part to model my problem. That okay, there is some generation of energy which anyhow created a force
Hmm.
which balances the all the opposite forces. This is like my thing, like so when it is moving when it is moving at 30 meter per second, same friction is acting, because friction is not like changing from by velocity. So at 60 meter per second also, like friction is same.
Yeah, so
So
there is
there
a
is a
that is my thing.
yeah,
yeah,
but there
but
is
there
a
is a
concept of
concept of
like
like
work,
work,
which is
which is
some
some
kind of
kind of
an
an
energy
energy
which is
which is
equal to
equal
the
to the
force
force
multiplied by
multiplied by
distance, I
distance,
think.
I think.
So if
So
there
if
is a
there is a
generation of
generation of
there is
there
some
is
kind
some
of
kind
work
of
done
work
which is
done which
going
is
in the
going in the
IC
IC
engine, and
engine,
which is
and which is
actually
actually
generating this
generating this
force.
force.
And this
And
D
this
is
D is
actually the
actually the
movement of
movement of
that
that
machine,
machine,
or
or
some
some
body, the
body, the
movement of
movement
this
of this
body
body,
which,
which
yeah.
yeah.
Actually, the problem is I am not able to communicate my doubt in proper words. That is, work done is same as energy. I can say, like, there's a
Yeah.
little difference in wording, but that is same. My question, I'm trying to formulate in particular line that at 30 meter per second there is particular friction, and there is particular force which is being generated by through engine. Now it is balanced and it is moving at 30 meter per second.
Okay.
Now at 60 meter per second, same friction is acting, same force is needed to balance it, to move it in uniform motion at 60 meter per second. So the force which is the resultant of the work of that engine is same at 30 meter per second, is same as at 60 meter per second,
No,
No,
force
because
will
we
force
need
will
not
to
be
not
same.
balance the same friction.
Force will
force will
not be
not be
same.
same. If
If the
the
body is
body is
moving with
moving
the
with the
higher
higher
velocity,
velocity,
then the
then the
inertial
inertial
force will
force will
not be
not be
same.
same.
That
That
we have
we have
discussed in
discussed
the
in the
previous
previous
cases.
cases.
We
We
saw
saw
that the
that the
velocity
velocity
difference is
difference is
different,
different,
and
and
then the
then the
inertial
inertial
force will
force
be
will be
different.
different.
So it's
So it's
not
not
like the
like the
same
same
friction
friction
force or
force
the
or the
same
same
inertial.
inertial.
Yeah.
No, but friction do not depend upon velocity, right?
Yeah,
Yeah,
but if
but
you
if
do
you
the
do the
force
force
balance
balance
analysis,
analysis,
you
you
may
may
have
have
a
a
different
different
friction
friction
force
force
due to
due
the
to the
different
different
inertial
inertial
force.
force.
For
For
example,
example,
let's say
let's
you
say
have
you
a
have a
body
body
here,
here,
and you
and
have
you
to
have to
balance the
balance the
inertial
inertial
force with
force
the
with the
friction
friction
force.
force.
Now,
Now,
if you
if you
change
change
the
the
inertial
inertial
force,
force,
then
then
your
your
friction
friction
force
force
may
may
get
get
changed
changed
depending on
depending
the
on the
situation.
situation.
So
So
let's say
let's say
do
do
one
one
thing.
thing.
Let's
Let's
go
go
one by
one by
one,
one,
because
because
then it
then
will
it will
be
be
jumbled up
jumbled up
in
in
every
every
case.
case.
So
Okay,
So
let's
okay.
let's
first
first
try to
try to
understand
understand
the
the
impulse
impulse
momentum
momentum
and
and
work
work
done.
done.
So
So
that I
that I
will
will
do in
do
the
in the
next
next
class.
class.
So
So
first,
first,
just
just
focus
focus
on the
on the
very
very
basic
basic
principles,
principles,
like
like
how there
how
is
there
a
is a
change in
change in
momentum,
momentum,
how the
how the
impulse
impulse
causes
causes
force,
force,
and
and
all.
all.
Then we
Then we
can
can
move
move
ahead with
ahead
the
with the
problem.
problem.
Then,
Then,
because
because
I'm
I'm
pretty much
pretty
sure
much sure
that
that
maybe
maybe
those
those
concept
concept
may
may
clear,
clear,
may be
may
able
be
to
able to
clear
clear
your
your
doubts
doubts
then.
then.
Sure, okay.
Yeah.
Yeah, so one request also, uh, like because of some issues, if I come across some other problems like after session, can I have, like, if you are comfortable, can I have your mail ID so I can also message you in a proper wording? Is that out? If it is
Sure,
okay
I-
for you, then
Sure, I've written down the email ID. You can mail me if you have some doubts.
oh, thank you very much. Thank you very much.
Okay. Okay, thank you.
Okay, so in the next session, like it will be work. Okay, thank you.
Sure.
Sure.
Yeah.
Yeah.
Thank you.